Starting off, differentiability. It's a great word, isn't it? Differentiability. Whether or not a function is differentiable. Okay, it's another one of these things like continuity where we don't really have to know too much. They sort of tie together. The only sort of thing that they might ask is, they might have a picture of a function and they say, is this curve differentiable at this particular point? Or something like that. And there's how you find out. It has to be not only continuous, but smooth continuous. So no sharp points. So another way of thinking about that, again, using notation that you don't really need to know that limit as a approaches from the negative side, a approaches from the positive side of the derivative needs to be the same. So it would be nice and smooth. So an absolute value curve would not be differentiable at 1. It is everywhere else, because it's nice and smooth everywhere else, but at 1 we've got a sharp point, so not differentiable at 1. And formally, as I say, you wouldn't be asked to do this, but I mean, formally you had to prove it. The limit as x approaches 1 from the negative side, well, that slope would be -1. From the positive side, it's +1. They're not the same, so not differentiable. As opposed to, say, this parabola, which is differentiable everywhere. At 1, if I approach it from the left-hand side, we'd get 1, and the right-hand side, we'd get 1 as well. Implicit differentiation is a fancy heading. Technically, implicit differentiation is in the Extension 2 course, when we give it the heading implicit differentiation. In reality, it's exactly the same as what we did yesterday, related rates of change, which is in the 3-unit course. But all of a sudden we call it implicit differentiation and we say, oh no, that's extension 2, that's extension 1. But it's the same idea. There it is. Exactly the same rule. If I want to differentiate a function with respect to x, I could differentiate it with respect to y and multiply it by dy dx. And where it's really useful is here we have x equals y squared, a parabola on its side. Now it's not a function with respect to x. So it makes it a bit hard. But I can still differentiate it with respect to x. Okay? Because what we're really doing when we differentiate, we don't normally write this line down. It's still an equation, x equals y squared. And we say, well, I'm going to differentiate both sides with respect to x. Now, normally on the left-hand side, you just have y. Differentiate y with respect to x, you get dy dx. And that's why you then write dy dx on the left-hand side. And then on the right-hand side, you go and differentiate that. So exactly the same here. We go, well, I'm going to differentiate x with respect to x. I'll get 1. Differentiate y squared with respect to x. Well, I can't do it. Right? I can't do it with respect to x, but I can do it with respect to y. And then if I multiply that by dy dx, well, the dy's would cancel, if you like, and I've got it. And so that's what we do. I'll say, well, okay, differentiate x, I get 1. Differentiate y squared, can't do it with respect to x, but I can do it with respect to y, so I'll multiply 2y by dy dx. And now I can rearrange this and make dy dx the subject, and there's our formula to find the derivative. But you'll notice we substitute in the y value rather than the x value for this one. And that's because the parabola is on its side. So if I substitute in an x value to find the slope, if it's a parabola on its side, I've got 2 possible points. But if I substitute the y value in, then there's only 1 possible point. So it works a lot nicer for that one. In fact, there are some functions where we use both the x and the y value. Imagine it was a circle. If I just used the x value, then I'd have 2 possible values. If I just used the y value, I would have 2 possible values. So in that one, I need to substitute in both the x and the y value to find the slope. If I had to differentiate this term, x squared y cubed, I'd have to use a product rule on it. So I'd write down the first, x squared, diff the second, but the second is y cubed. Okay, I can differentiate it, but it's with respect to y. So I'll do that, 3y squared, but then I need to multiply by dy dx to balance it out. Plus, write down the second, y cubed, diff the first, well, that one's okay, I can do that with respect to x, it's 2x. And just tidying that up, there you go. We get that sort of expression when we differentiate the particular term. So all right, I talked about the circle before. Let's say we did have to go and find the equation of the tangent to a circle at the point 1, 2 root 2. So x squared plus y squared, differentiate it. Okay, x squared, that's not a problem, 2x. Y squared, well, I can't do it with respect to x, but I can do it with respect to y. So I'll make it 2y dy dx, and then on the other side, we'll differentiate the 9, we get 0. Make dy dx the subject, eventually we get, there it is, minus x on y. So as I was saying before, with the circle, in order to get a unique one, we're going to have to put in both the x and the y value. So sub in the x and the y value, we get minus 1 on 2 root 2. There's our point, there's our slope, and just like we always do, point slope formula. We don't change it, it's the same point slope formula as always. So y minus the y value, slope x minus the x value, and tidying that up, I've got it in general form, but there's the equation of the tangent at that particular point. Now that's the beauty of what we call implicit differentiation. I suppose this is the part where, okay, that's not an extension 1. They're not going to ask you to find the equation of a tangent to a circle. Okay. Extension 2 they might, and other conics that we look at in extension 2. But really, it's no different, as I say, to the idea we looked at yesterday, using that idea that to find dy dx, you could break it up into 2 different rates and multiply them together. We can find other derivatives. Chain rule, that's all it is. Chain rule, related rates, implicit differentiation, it's all the same thing. For some reason, we just use different names depending on the type of problem that we're solving. So all right, we'll have a go at sum out of 7k.